Hi everybody, I'm Gabe. I'm here to tell you about Depthcharge, which is the Chrome OS Bootloader. It's a payload for core boot. So the design goals for Depthcharge, there's a single focused goal, which is to just boot Chrome OS, not to boot other operating systems or perform other jobs. And because it's got a focused, specific goal that helps to make it achieve the other design objectives, which are for it to be small, which makes it fast to load out of the storage as you boot. It's relatively easy to learn because the code base is smaller. It's harder to attack because there are less things to screw up and prevent or present bugs to attackers. It's simpler, which gives you faster execution time because it has to do less work. It's easier to think about because the things that it's doing are less complicated. And you just have better productivity as a developer because you have to do less stuff. And I've also tried to make it as efficient as it reasonably could be, well without sacrificing too much on the other goals. So the code flow when core boot hands control over to Depthcharge is first that it'll enable some consoles, sets up some timekeeping mechanisms, and then it calls into some initialization callbacks. And then right from that point, it calls into the verified boot library, which I believe has been talked about already, in 3 different ways. It first initializes the library, then it asks the library to choose which version of the firmware it should use from that point forward, and then it asks the library to choose which kernel to run. And that third step is where most of the interesting things happen, and that's where it might present the developer mode screen if you're in developer mode, or it might perform the recovery flow if you got into recovery mode for some reason. And all 3 of those steps will call back into Depthcharge when it needs to do something specific to the platform. So for instance, when it decides that it wants to load a kernel from disk, it'll say, well, Depthcharge, please load from this disk this many blocks in of a blob of a particular size. And Depthcharge will do that and then hand the data back to vboot. And then once all of those steps are performed, there's a kernel that's been loaded into memory and selected by vboot. And Depthcharge will unpack it, get it set up to run, and then actually start it. I would like to make a minor correction to Stefan's presentation. At least in the case of Depthcharge with Chrome OS, the device tree comes from the blob that has the kernel in it rather than the firmware itself. But it is chosen by the firmware. And in other situations, the firmware would need to provide it. So as has been mentioned in several other presentations, there's a library that's provided for payloads called libpayload. And this is a BSD licensed collection of functionality that's useful for payloads in general. You can think of it sort of like a standard library with a few extra things thrown in. There's the standard support code sort of thing, like memory management, malloc and free. There's a printf implementation, string functions like memcopy and memset, random number generator, udelay, et cetera, et cetera. There's LZMA implementation, PCI utility functions, and CBFS, which I don't know if it's been explained, pardon me if it has, but it's basically a data structure that's in the flash that core boot uses to keep track of different pieces of information. And then it also provides a number of drivers. There's a USB stack, or several USB stacks provided there, and a USB keyboard driver, a PC keyboard driver, USB mass storage implementation, support for USB hubs. Then it has a number of interface implementations. There's a CBMEM console, which is an in-memory console buffer, so that after the system boots, if you had no output turned on, you could see what messages there were from the firmware. UART drivers and video drivers. And it also can talk to CMOS and PC keyboard, as I mentioned earlier. So the code structure in Depthcharge itself is fairly straightforward. There's a top-level directory called board. And what that does is it gives you a place to put the configurations for a particular board and also how all that, this is probably something that doesn't really belong in Depthcharge itself, but is there for historical reasons. Something that shows you in the final image as it's laid out where all of the pieces go. So there's resources like the images that are shown on the screen during developer mode, and the different copies of the firmware, and there's a file that's called fmap.dts, which shows where all of those pieces go and how much space they're allocated and that sort of thing. And then there's the actual source for Depthcharge, and there's an Arch directory which doesn't have a lot in it, but it's for architecture-specific code, base directory for generic code, board, and this is in contrast with the other board directory more for actual implementation. So the outer board directory is for configuration information, and this one is more for implementation. But it is a little bit of configuration. I'll talk about that later. Then there's boot, which is support for booting a Linux kernel. There are drivers, which are all the driver implementations. Image, which is code for managing the image of the firmware itself. To find those pieces in the image is laid out by the fmap.dts. There's net, which is a network stack, a modified version of UIP, which is used for network booting, which we use in our factory process. There's a netboot directory, which has the implementation of TFTP boot. And then there's the vboot directory, which is where the code is that calls into vboot and then receives calls back from vboot and distributes them to the other parts of the payload. So one of the largest portions of code in Depthcharge are all the different drivers that it needs. Those are organized as sort of reminiscent of the Linux kernel as at the high level, a series of structures which have callbacks in them that are generic, and then and each of those callbacks accepts a pointer to the generic interface object as its first parameter, sort of in C++ like the this pointer, which refers to the object that a method was called on. And then those structures are embedded within a larger structure which has the information for that particular device. So for instance, if you had a UART and you needed to keep track of what speed it was supposed to run at and what, let's say it's a PCI device, what its PCI device number is, that information would go in the larger containing structure. And then the generic interface structure would have something simpler like print or read. And those would be the normal interface. And then there's a macro called container of, which is similar to what's in Linux again. And what this does is it lets you move from the embedded structure back out to the larger structure. So the implementation of that particular UART would be able to say, okay, here's a pointer to this generic interface, which is what my caller knew about. But I need the information that's in my version of the structure so that it can basically do a subtraction and move out to the larger data structure to get the additional information that it needs. So one of the principles that these drivers are oriented around is to be as lazy as possible. Only do what you're asked to do at that particular point in time, and don't set up a device if you're not being asked to use it. And this is very useful for performance perspective. So for instance, if you're booting in normal mode on Depthcharge, you don't have to talk to USB devices. You don't need to look at USB storage. You don't need to look for USB keyboards. So if you're not going to use that functionality, the time it takes to bring up the USB and to enumerate all the devices on it is basically a waste. You're not going to use that information. So if nobody calls into those functions, that will never happen. And you don't have to try to figure out ahead of time, well, is this something I'm actually going to need? You just wait until you're asked for it, and then you know whether or not you're going to need it. And these structures are returned by functions that are called new underscore and then the name of the driver. And what these do is it lets you set parameters in that larger structure. So for instance, when you have a particular PCI-based UART, you could, when you initialize the structure with this new function, pass in what the device ID is that you want it to be at. And similar to the principle above, these new functions don't actually initialize. This is a common misunderstanding. These new functions don't initialize the device and prepare it for use. They just set up the parameters which describe the device so that later when somebody tries to use it, those can be used to get it going. So if you look in the source driver directory, there are classes of devices, for instance, UARTs or SPI controller drivers and that sort of thing. And they're generally organized so that there's a directory that contains that class of devices. And then there's the file called that class.h and that class.c, and those contain the generic structures which I talked about earlier, which have the callbacks. And then perhaps, not necessarily always, but some small amount of implementation which helps to support that class of devices in general. And then alongside those files would be all of the implementations of the specific drivers that are necessary. So here's an example of the generic header from the drivers which control rebooting and powering off the system. At the top you can see a structure called power ops. And this has two callbacks within it, one called cold reboot, which you can imagine what that does, and one called power off. And these both take as their first parameter, as I mentioned earlier, a pointer to a power ops structure. And then there are some functions below it, since, for instance, when vboot calls back into Depthcharge, it doesn't have the idea of drivers. It'll just say, I want to turn off the system now. And the way that that's implemented is there's a function called power off, and it calls that. And before, when the system is being set up, there's a function called power set ops. And you tell it, when somebody asks you to do something power related, use this driver. And then these implementations will know to call into that particular driver. Then here's a large portion of the implementation of this driver. There's a couple functions that I left off, but this is probably about 2/3 of the driver. As you can see, it's relatively straightforward. There's the set ops, as I was describing before, and then there's a cold reboot function, which this is an implementation from a driver which talks to the system's PMIC, I believe. Oh no, excuse me. This is just the function that calls into the driver itself. I'm sorry. So you can see where it does a little bit of work, and then it calls into the power ops driver, which has been set earlier at the bottom. Power ops arrow cold reboot, and then it passes in the driver. So here's the header for a particular implementation of this interface. You can see that there's a structure which is more specific, which describes, this is the AS3722 PMIC, which is on the Tegra device, which was alluded to earlier. And you can see that there's a power up structure which is embedded within it. And this is where those generic callbacks would go. And then it also needs an interface to the I2C bus that it's going to be on, and a chip ID. Now you can see that the power ops is actually embedded directly into the structure, but the I2C ops is not. And that's because the I2C ops is an implementation provided by another driver, which is the I2C controller. This driver will call into that through the generic interface. So you can chain a series of these drivers together so that you don't have to have known ahead of time, well, I'm going to have this driver, and this is the only way that you can call into this driver. You can say that it's behind an I2C bus, which is behind a PCI bus, which is arbitrated with this GPIO. And all of those things can be put together on a case-by-case basis as necessary, which is occasionally very important. And then finally, there's the prototype of the new A2S or AS3722 PMIC, and it accepts the I2C driver and the chip as a parameter. And here's the implementation of that driver. This is actually what I was describing earlier, where this is about 2/3 of the driver. There's a few utility functions above which aren't shown. But looking at the cold reboot, for example, what it does first is it uses the container of macro to extract the containing object, which has the extra information that it needs. And then it calls in, it uses the bus parameter, which is the I2C bus interface, and the chip, which are stored in those in that structure, to request that the PMIC power the system off. Or excuse me, in that case, reboot it, in the case below, power it off. And then at the end of the file, you can see that there's a new function which will allocate the structure which describes the driver and set the callbacks and the information that was passed in, the bus and the chip, and then return the larger structure. And before I move on, does anyone have any questions about how drivers are set up or how they work? Yes? So that I'll kind of get to later. There's a function which sets up all the information about a particular board, and for instance, on a lot of devices that use I2C buses, there will be lots of instances, and those would be more parameters to other drivers. And then those other drivers, for instance, if you had a flash chip, which would be behind a SPI bus, you'd attach the SPI bus to the flash chip, and then there are generic functions for accessing the flash storage. And the flash driver would be plugged into the generic storage. Generally, you have to kind of narrow it down to one particular device, which is supposed to provide a particular service. That's not necessarily true of storage, because you can have fixed storage and you can have removable storage like USB keys, where there might be multiple instances. But in that particular case, the vboot library has an interface which requests a series of devices, and then it can talk about individual devices within that list. So that's kind of a special case, but most of the time you have to narrow it down to one particular client. Anyone else? No? Okay. So this was what I was alluding to just a minute ago. There's a board setup function, and this is the board setup function from the Pixel Chromebook. The Pixel Chromebook doesn't actually ship with Depthcharge, but Depthcharge was developed to support it. So at the top, there's a utility function, sysinfo install flags. We don't need to worry about that. The next line is it's allocating a GPIO driver or instantiating it, and those are the parameters which say which GPIO it's talking about. I believe that's a bank and a GPIO index, and then it's installing that as the GPIO to read information about whether or not the EC firmware is in its updated read-write copy or in its read-only. Then next is instantiated a driver for the LPC bus, which is specifically for talking to the EC. It's sort of an adapter to talk to the LPC protocol for the EC. Then that's set up. Then, as I was mentioning before, there's an interface for talking to flash, and so a driver is allocated for the memory map flash, and that's installed. Then sound driver is installed. Storage driver is set up and attached to the list of storage devices. Power is set up, and then the TPM is set up. x86 x86 Chromebooks tend to be more simple in their configuration because devices are more discoverable, and there tends to be fewer pieces, or at least pieces that need to be worried about at a software level. There might be more buses, and things may be memory mapped, so you just have to know where things are. But here you have to kind of construct a bus hierarchy. Or excuse me, in the ARM case, you have to construct a bus hierarchy. So ARM board setup files are generally longer. And I picked this one because it fit on the slide. Does anybody have any questions about this particular step? No? Okay. So how do you configure Depthcharge? It's configured using kconfig, which people are familiar with. Generally, all of the settings are set to off. And then in that board directory I mentioned earlier, there's a file called defconfig, which you can use to, it's kind of unfortunately named, but you use it to override the defaults, which are off. So it looks like just a list of the things that you want. And then kconfig is called into with I think the defconfig target, and it will take those and then override the defaults as you've described there, and then everything else you don't have to worry about. So for instance, on x86 Chromebooks, you don't have to worry about configuring ARM-specific features. On ARM-specific or ARM Chromebooks, you don't have to worry about configuring parameters for other chipsets that you don't care about. Those things are just all off and out of the way and inert, and then you can enable the things that you want and configure them. And generally speaking, this level of configuration is to turn on the availability of something. So for instance, you need a particular driver for an I2C controller. This will make that driver available, but the configuration that sets the parameters of the driver are done with those new functions. And that helps to address the situation where you have multiple instances of a particular driver that need different configuration values. kconfig doesn't handle that very well. So here is the kconfig for the Pixel Chromebook. And as you can see, it's relatively short, and since this was written out by hand, there are comments that say what each of these different sections are for. It's pretty straightforward. The largest part is generally the list of drivers at the end. And I'd imagine that this, does anyone have questions about this? This part is pretty straightforward. No? Okay. So then if you look at the, what functionality is just generically available to support boards, there's a concept of init functions, which are collected into a linker set and called one after the other early in the board setup, or in the Depthcharge setup. And there's one of the primary uses of that, nearly the only use of that, is the board setup function, which I described earlier. That's how that's called into. But you could add other ones if you wanted to. And those are not supposed to touch hardware. So for instance, if you have driver, you wouldn't set up one of these initialization functions to query the device and get it going. That, as I said before, is what you're supposed to do when you actually try to use the driver. Then there are cleanup functions, which sort of have an opposite purpose. These are installed, and they're called when Depthcharge is about to leave for some reason. For instance, if it's about to exit Depthcharge and boot into the kernel, or if it's about to reboot the system for some reason. So you can clean things up, or for instance, if you have a video driver that's doing DMA, but when you get into the kernel, the kernel is going to set up some sort of translation of an IOMMU of some sort. That DMA could interact with the IOMMU and cause the kernel to panic because the kernel didn't expect that to be going on at that point. So you could install a cleanup function which would say, when you're about to go to the kernel, just give me a second and let me turn off that DMA so that the kernel doesn't die. Then there's linked list implementation, container, of which I already mentioned. There's a directory called device tree, which has an implementation of a simple device tree library, which lets you read in the device tree of the kernel and manipulate it in whatever way is necessary, and then timestamps for performance measuring. And if you wanted to support a new board with Depthcharge, it's a relatively straightforward process. Basically, you copy or you create a new board directory, top-level board directory. You need to add an fmap.dts, which says where everything goes. You can generally copy those from something else that's similar. Then you would create a source board directory, which is the inner one, which has the board setup function. And then you'd modify kconfig so that it could find it. And then you'd add a configuration file, defconfig, enable the drivers that you need. If it's an existing chipset that's already supported, there's probably already all the drivers that you would need. But if not, then you'd need to implement those missing drivers and enable them. And you'd write a setup board function which would glue all those pieces together. And then you'd repeat as necessary because this probably forgot something or something doesn't work. Relatively easy. So does anybody have any questions about that portion? Yes.
So when you have the missing drivers, do those go into libpayload?
So it depends. Libpayload was originally implemented, Record Boot, and I don't want to say it was originally implemented to support specifically x86, but has historically supported primarily x86. And libpayload has historically, I think, been focused on x86 as well. And on x86, there's lots of legacy low-level drivers for things that have been in there since the 80s, and it's easy to support with a single timer implementation the timers on x86. On ARM systems, that's not as true. Each SoC generally has its own timer implementation, its own UART implementation. So on x86 systems, libpayload provides drivers which are used within Depthcharge. On ARM, that's not as true. So if you were on an x86 system, you might add those drivers to libpayload because they might be universally useful. On ARM, you might not. Now, there are some things which I think we were second-guessing that decision and might move into libpayload, specifically the timer and UART implementations, because those are more fundamental. As you're getting going, you really need to be able to send console messages because you can't get very far if you can't see what's going on, and sometimes delay is a really necessary thing to have right at the beginning. So we were thinking about moving those into libpayload. It's sort of an undecided question, but I would say that's my answer in general.
Well, there's also a licensing issue too, because libpayload is BSD.
Yes, that's,
The drivers you're going to be porting are going to be coming from Linux kernel or GPL.
yes, that's very true. So Depthcharge itself is GPL. So if you wanted to move drivers into Depthcharge, that's not as big of a concern. That has come up in the past, where there are drivers that we had wanted to put into libpayload, but were unable to because they weren't BSD compatible. But that's a very good point. So if you have drivers that are BSD compatible, you can put them wherever you'd like. If they're GPL'd, then you probably only have one choice. Any other questions? Yes?
So the lazy initialization approach you mentioned makes a lot of sense when you're not going to end up using a device. If you know you are going to end up using a device and it has long delays in its initialization, is there a process for eagerly initializing a device so that its delays can happen in parallel?
Yeah, sure. One approach to that is that you might start the initialization in core boot. So for instance, the video is a device like that, getting an LCD panel going, because the boot times for Chromebooks are very short. So the amount of time you have to sit around and wait for the power to level out on an LCD is relatively a very long time. That happens in core boot. It'll start it up, and then it'll do something else, and then it'll maybe get back to it and do a little more with it. In Depthcharge itself, there isn't really a mechanism to handle that because that's not as common. It really is, I would say, a strongly held principle to do things lazily, but it isn't an architected rule. So if you have something where it just really makes sense to do it a different way, there wouldn't be anything architecturally that would prevent you from doing that. Anybody else? Well, that's all the material that I have to present. I don't know how I'm doing time-wise. About 15 minutes into my allocated time. Well, I'll be sitting over there if anybody has any other questions. Otherwise, I'll hand it off to the next person.